Now let us do a small problem with constant strain triangles. So we have this square domain, which for simplicity we have taken to have dimensions 1 cross 1. One side of the domain is subjected to distributed traction of magnitude P naught, and concentrated loads are applied P by 2, P by 2 at these two corners. The boundary conditions, the other boundary conditions are as shown, and there are 4 elements that have been used. 1, 2, 3, 4 are the numbers, and these are the node numbers that have been given. Now these are constant strain triangles. Each of these are constant strain triangles. We are not going to talk about the assembly process and so on. So we will first see how we can calculate the stiffness matrices and the force vectors corresponding to these constant strain triangles. A generic constant strain triangle, let's say triangle number 1, constant strain triangle number 1. Okay, so the first task and the most important tasks are to calculate N, which we have seen is a 2 cross 6 matrix, and B, which we have seen is a 3 cross 6 matrix. Once you have this, you can calculate KE, which in this case would be a 6 cross 6 matrix, and FE, which consists of FBE and FSE, the surface and the body force part. So these are 6 cross 1 vectors, where FBE is 0 in this case because there are no body forces in any of the elements. FSE is present. So KE is calculated by this formula. FBE is 0 for this case, and FSE is present only if the element shares an edge with the boundary of the body on which tractions are applied. So if it shares an edge with delta Vt, then only FSE comes into picture. This is true only for element number 3. Element number 3 shares this edge with the edge of the body on which tractions are applied. For all other elements, FSE would also be 0 except for element number 3. So so these are the things that we need to do, and as we have mentioned in the last lecture, when we use the assumed displacement method, the shape function matrices are calculated in this manner. So we first form this 6 cross 6 capital A matrix, which is formed by the elemental nodal coordinates, and then we have this, which comes from the assumed displacements that we have taken, which comes from the fact that we have taken displacements which are linear in x and y, and that's how we get this matrix. And the product of these two matrices gives you the N, which is 2 cross 6. So this is 6 cross 6, this is 2 cross 6, and we get a 2 cross 6 N matrix. Now this is one possibility. You can take the nodal coordinates of the nodes, of the 3 nodes connected to the element in question, and you can do this procedure. But for linear triangles, for triangles that we call as constant strain triangles, we have a easier process available. I will first give you the recipe of that process, and then talk about how this has been motivated. Okay, now let us name the element nodes. So let us have this generic element, which we call E, and let the nodes be called I, J, and M, having coordinates xi, yi, xj, yj, and xm, ym in the global coordinate system. Now, first, to calculate the shape function at node I, we will take these coordinates and calculate three constants, ai, bi, and ci. Ai depends on yj, xj, and xm, so it depends on the coordinates of this node and this node only. Similarly, bi depends on yj minus ym, again on the y coordinates of these two nodes, and ci depends on the x coordinate of these nodes. Apart from this, we will have to calculate the area of this element, and this area of this element is known if you know the nodal coordinates, and you might be familiar with this formula. You can take determinant of 1 x1 y1, 1 x2 y2, 1 x3 y3, and you get twice the determinant. Once you have got this area of the triangle and these three constants, you can calculate ni, which is the shape function defined at this node. And this ni is given by ai bix plus ciy divided by 2 delta. So this is a easy relation which embodies everything that you would do in this multiplication here. Here you would multiply this matrix with the nodal coordinate matrix, and this is a compact way to perform that operation and get n1, n2, n3 out out of that calculation. Now, where does it come from? It comes from a very simple consideration, and the simple consideration is known as area coordinates, where for a triangle, the three areas are defined. Suppose you want to find the shape function at this point P, which has coordinates x and y. Then I define three areas. So the area A1 is opposite to the node 1 and is formed by nodes 2, 3 and the point P. So this is the area A1, and similarly area 2 is opposite to 2 and area 3 is opposite to 3. Once you have these areas, you define N1 as A1 divided by the total area of the triangle, N2 as A2 by total area of triangle, and N3 as A3 divided by total area of the triangle. It is easy to now see that these will naturally satisfy the Kronecker delta property. What is the Kronecker delta property? Say the shape function 1 should be 1 at this point, node 1, and 0 at these 2 points. So when this point P lies on 2, obviously when this point P lies on 2, obviously A1 becomes 0. A1 becomes 0. When it lies on 3, A1 becomes 0 as well. So N1 will be 0 whenever P lies on XY lies on either node 2 or node 3. And when it lies on node 1, then the whole triangle is A1, A3 and A2 become 0, and that's when N1 is equal to 1. Similarly, you can check it out for N2 and N3, and you can see that they satisfy the Kronecker delta property when they are defined like this. Also, summation of the three N1, N2, N3 would simply give you A1, A2, A3 by delta. A1, A2, A3 is the whole triangle, so this is obviously equal to 1. So the partition of unity property is also satisfied. So this concept of area coordinates, where you define the shape functions as ratios of area divided by the total area of the triangle, is actually embodied in these calculations for which I have given you the recipe. So if you follow this recipe, you would actually be doing the area coordinates and finding the shape functions. So this is a direct way of finding shape functions without actually undergoing that A inverse times a matrix, that calculation that we showed. It's the same calculation done in a more systematic way. Now, if you remember this basic equation where the shape functions interpolate the nodal variables to any point, to the field variables at any point. So this is uxy and this is vxy. To get uxy and vxy at any point inside the element, you would need the shape functions which will operate on the nodal quantities. So remember that u will be equal to n1 u1 plus n2 u2, n3 u3, and v will be n1 v1 plus n2 v2 plus n3 v3 for our triangular element, and the shape function matrix is n1 0 0 n1, n2 0 0 n2, and n3 0 0 n3, whereas the capital U is u1 v1 u2 v2 u3 v3. This is the capital U. So the first row into this gives you this equation. Second row into this gives you the second equation. So n times u is what I have written, and that is equal to small u. Right? So these two equations are written like this. That's why this is a 2 cross 6 matrix. Now I have n1, n2, n3 directly, and therefore I can actually write them down. But before writing them down, let us take some actual values. Let us take node number, element number 1. So let us call this as its local node 1, local node 2, and this is local node 3. So local node 1 has coordinates 0 0, local node 2 has coordinates 1 0, and local node 3 has coordinates half half for this particular element 1. So if for this element 1 you want to calculate the area of the element, so remember it is determinant of 1 x1 y1, 1 x2 y2, 1 x3 y3. So x1 y1 is 0 0, x2 y2 is 1 0, and then half half. This determinant will give you 0.5. So 0.5 by 2 is the area of the element, and then you calculate n1, n2, and n3 by using this formula. So first you calculate a1 b1 c1, a2 b2 c2, and a3 b3 c3 for the 3 nodes, and then put them in to get n1, n2, n3 for the. So this, if you simplify, would become 1 minus x minus y. This would become x minus y, and this would become 2y. And now plug it back into the n matrix. So this is 1 minus x minus y, this is x minus y, this is 2y. So this is your n matrix, first row of the n matrix. In the second row, this is n1, this is n2, this is n3. This is your n matrix completely. So now that you know the n, you know u is equal to n1 u1 plus n2 u2 plus n3 u3. This is my basic guiding principle. So del u del x is del n1 del x. u1 is a constant. So del u del x corresponds to this first line of the B matrix, first row of the B matrix. So del n1 del x is minus 1, del n2 del x is 1, and del n3 del x is 0. So minus 1, 1, and 0. The second one is for V. So V is n1 v1 plus n2 v2 plus n3 v3. So del V del y is del n1 del y v1 plus del n2 del y v2 plus del n3 del y v3. Then del n1 del y is minus 1, del n2 del y is minus 1, del n3 del y is 2. So this is del n1 del y, del n2 del y, del n3 del y. And then for epsilon xy, you need to calculate del u del y and del v del x. So del u del y will involve del n1 del y, del n2 del y. So del n1 del y is this, del n2 del y is this, del n1 del y is this, del n2 del y is this, and del n3 del y is this. Similarly, this will involve del n1 del x, which is this, del n2 del x, which is this, and del n3 del x, which is this. So if you have formed the B matrix, so that multiplying this with u1 V1, U2, V2, etc. will give you epsilon, which we have defined, remember, as epsilon xx, epsilon yy, to epsilon xy. So this is your strain displacement matrix, and now that you have got N and B, you have all the ingredients required to form the stiffness matrix as well as the right hand side vectors. Okay, so to do that we need to now know whether it is a plane stress problem, plane strain problem, or an axisymmetric problem. There would be slight differences from now on. Especially let us understand what it means for an axisymmetric problem. For an axisymmetric problem, what we have here uh, is we will interpret this x-axis as the r-axis and the y-axis as the z-axis. So this is the RZ plane of an axisymmetric body, which can be rotated about its z-axis to get its solid of revolution. So what you are looking at is actually a radial section, of a cylinder which is 1 in height and 1 in radius. So it's a cylinder which has a radius of 1 and a height of 1. That's what you are looking at when you are thinking of this as an axisymmetric problem. And the top part of the cylinder is subjected to this load. So what you are basically looking at for an axisymmetric problem is a cylinder of diameter 2, height 1. This is your z-axis. This is your r-axis, or sorry, this is your r-axis. This is your r-axis, and then we are looking, so this is 2, the height is 1, it is subjected to a uniform pressure P0 on the top surface, and what you are trying to simulate is a section like this. This is the section that you're simulating, trying to model, and this is divided into four triangular elements. So this shaded part is what you see here. If you think of this as an axisymmetric problem. Now in an axisymmetric problem, we do a small addition to the B matrix, and it is this. In plane stress and plane strain cases, our epsilon is epsilon xx, epsilon yy, and 2 epsilon xy. This is our epsilon. In the axisymmetric case, we often define epsilon with an additional rho. So epsilon, this is epsilon xx, which is same as epsilon rr. This is epsilon yy, which is same as epsilon zz. This is epsilon xy, which is same as epsilon rz, and we add an epsilon theta theta. We don't do that even for plane strain, where epsilon zz is present, because epsilon zz is simply connected to epsilon xx and yy. It doesn't need to be solved separately. But in axisymmetry, we sometimes add this last strain, and therefore your B matrix, which is the strain displacement matrix connecting the strains to the nodal displacements, the B matrix is now 4 cross 6 rather than 3 cross 6. This is still 6 cross 1, and in axisymmetric case it would contain the nodal, in the axisymmetric case this would contain the nodal displacements UR1, UZ1, UR2, UZ2, and UR3 UZ3. So these will be the displacements that would be nodal displacements that would be contained in U. B would relate that to the strains. There are 4 strains, therefore you would need, this is 4 cross 1, so you would need 4 cross 6 B matrix. The last row of the B matrix corresponds to the epsilon theta theta stress. Now if you remember your axisymmetric coordinates, you would remember that for axisymmetry, when things are independent of the theta direction, epsilon theta theta is equal to simply UR by R, and UR we have written as N1 UR1 plus N2 UR2 plus N3 UR3 divided by R. And now in our problem, this is the z-axis, so whatever is the x coordinate of a point is actually the r coordinate in case of our problem. So any on element number 1, if this point has coordinates xy given, we can interpret this as rz if this is an axisymmetric problem. Therefore x is replaced by r is replaced by x, r is replaced by x, and then therefore I can write these as n1 by x ur1, n2 by x ur2, and n3 by x ur3. These are usual. So for epsilon theta theta, in axisymmetric case, we will add this, this, and this. They get multiplied with UR1. They don't get multiplied with UZ1. They get multiplied with UR2, not with UZ2. They get multiplied with UR3, not with UZ3. So you have zeros in place of the z's, and the shape function by x in place of the r's. Okay, so now this is the same B matrix apart from this new line that has been added, new row that has been added. So this is the first change that you need to do when you go from plane stress, plane strain, which have the same B matrix that we showed in the last slide. This B matrix holds for plane stress, plane strain, and for axisymmetry you add this epsilon theta theta and you have a new row. Now the stiffness matrix is local stiffness matrix for the element is an integration over the volume of the element times B transpose CB dV. This dV will be interpreted differently in case of plane stress, plane strain, and axisymmetry. So in case of plane stress, you might be supplied with the thickness of this element. So your element, triangular element, may actually have a small thickness which is T, and therefore an small element which has area dx dy has volume T times dx dy. So in plane stress, this is the dV that you will use. In plane strain, we generally have infinite thickness in this direction, and we solve things per unit thickness. So this T is equal to 1. So you use 1 times dx dy as the volume, and that's what you would replace here. So you would replace 1 times dx dy as the volume here. In case of axisymmetry, you are actually solving for a triangular cross-sectional toroid. So this toroid, this is the element, and then this is actually rotated around this axis, and this is the shape that you are solving for, so that if you take a small element now which has dx dy in the plane, dx dy or dr dz in case of axisymmetry, and you are and its radius is x, then the volume dv is 2 pi x dx times dy. So this is what you will use for axisymmetry. So this solution is exactly the same for plane stress, plane strain, and axisymmetry, except for the definition of this elemental volume, which is different in the three different cases. Okay, so there's one more difference that we have to take into account, and that difference is something that we have discussed before, is the definition of this matrix C, which is different for axisymmetric, which is the stress strain relation, which is different for plane stress, plane strain, and axisymmetry. So in case of plane stress, this is what you have to use. We have discussed this before. In plane strain, remember the stresses that we are using are also sigma xx, sigma yy, and sigma xy for plane stress and plane strain. And for axisymmetry, we are using sigma rr, sigma zz, sigma rz, and sigma r theta in case of axisymmetry, which actually map to sigma xx, sigma yy, sigma xy, and sigma zz probably in the xy if we replace r by x and z by y. Okay, so we have four stresses connecting four strains. So we have a 4 cross 4 stiffness matrix in case of axisymmetry, 3 cross 3 for both plane stress and plane strain. So you do this now. So now you have these small points of difference. One is a new row is being added to the B matrix. The definition of dV is different, and the C matrix that you use has to be chosen. Apart from that, the whole procedure for plane stress, plane strain, and axisymmetry are exactly the same. Now let us come to the forces. When we are considering element 1, there are no edges on which loads are applied. There are no body forces, so there are no force components that are being generated by this element. The only forces that are being generated by any element is element number 3, which has constant force, constant distributed load going from between nodes 4 and 3. 4, remember, has coordinates 0, 1, and 3 has coordinates 1, 1. And so we have to take an edge load on this surface. How will we handle it? So let us look at this. So this is how we will generate the surface load. So the surface in this case, if you consider, let's say, plane strain, the surface ds is actually dx. If you look at it, it's actually dx, and dx goes from 0 to 1, and t is tx, tx is 0, ty is minus p naught, and n transpose, n we have already calculated, and n transpose is 1 minus x minus y, 0, 0, 1 minus x minus y, then x minus y, 0, 0, x minus y, 2y, 0, 0, 2y. This is your n transpose. So this is n transpose. We're calculating this. We'll integrate from 0 to 1 of dx, and that will give me the elemental force vector. Now what we should expect is that there are nodal forces acting on degrees of freedom 8 and 6. So p by 2 will be present in nodal degrees of freedom 8 and 6 anyway. And apart from that, you should have nodal loads corresponding to this distributed load, which will also be distributed to degrees of freedom 6 and degrees of freedom 4. Apart from that, there are no forces anywhere, so no other nodes. should get any contribution from these applied loads. So when you assemble the loads, when you formulate the you first formulate the load vector for element number 3. All other load vectors from element numbers 1, 2 and 4 are 0. Then you assemble the loads, and when you do that, this is what you should get. This is what you should get. You should have an you should have something in degree of freedom 6, you have something in degree of freedom 8, and everything else should be 0. And for this element ds, for this element ds that we have, it is equal to dx in case of plane strain. It will be t times dx in case of plane stress, and it will be 2 pi x dx in case of axisymmetric. So the ds will be different for different cases. For axisymmetric, what we have is the load applied over this whole thing. So this load is at a distance x from, so would be 2 pi x times dx would be the area on which this elemental load is applied. Then you integrate it from 0 to 1 and you get the total load applied. So this will be your total load vector, and the assembled stiffness matrices, you will have to assemble these stiffness matrices between elements 1 to 4, and you will get the assembled global stiffness matrix. Now we can have a higher order version of this element, which means that instead of using 3 nodes per element, we can use, let's say, 6 nodes per element and add a node at the middle of the edges, and now we have 6 nodes and 2 degrees of freedom per node. Therefore we have 12 constants that we can determine, and these are the 12 constants that we have chosen. Again, as you can see, that we have tried to take these two balanced polynomials, in the sense that the polynomial terms used are the same for u and v, and then you will be able to see that if you take first x derivative of this, this term becomes a constant, this goes to 0, this remains, and this remains, this goes to 0 again. Similarly, when you take derivative of this with respect to y, a9 remains, a10 vanishes, a11 remains, a12 remains. Similarly for xy. So all these will give rise to linear strains. So this is called LST, or a linear strain triangle. Contrast this with CST, which allows you to approximate constant strains over the region of this triangle, whereas this allows you to use linear variations of strain. So the procedures leading to the stiffness matrix of this element is exactly the same. The calculations are just a little bit more tedious. Forming the shape functions for these nodes will be slightly more challenging than for the corner nodes, but apart from that, the procedure is exactly the same, and you can try it out as an exercise.